From International Journal of Heat and Mass Transfer, Elsevier. Flow and heat transfer characteristics of single jet impinging on protrusion surface. By Di Zhang, Wancheng Ku, Jiabing Lan, Jianhui Chen, Yonghui Xie. Study on the flow structures. The vorticity of impinging jet flow on protrusion target surface at variable relative depth when d equals 0.318 and Re equals 5000 is obtained as shown in Figure 1. The coordinates z, r represent the axial and radial direction, respectively. The shaded areas indicate the location of the protrusion. High axial vorticity areas are considered as the position, transitional region, where jet core and surrounding fluids interact. The high vorticity is generated by the strong momentum and mass transfer at velocity discontinuity surfaces resulted by the large velocity gradient in radial direction. And the radial high vorticity is in the transitional region between the surrounding fluid and the wall jet. The PIV results have not captured the mini-separation flow in the transitional region between protrusion and target surface. The PIV particle medium would not have been distributed uniformly in the transitional region between protrusion and target surface. There would be less particle medium photographed by the PIV system. And so the mini-flow separation would not be observed in the PIV test. However, the CFD and experimental results reveal a close agreement in terms of vorticity. As protrusion relative depth increases, the turning angle between protrusion and target surface increases, which results in flow separation in this region. Moreover, the size of flow separation rises when protrusion relative depth rises. Furthermore, comparison of results between PIV experiment and CFD reveals that the flow structures on protrusion surface when Re equals 10,000 and 23,000 are similar with that of Re equals 5,000 at D equals 0.318. The only difference is the vorticity magnitude and the size of flow separation in the transitional region between protrusion and target surface when Re differs. In detail, higher Reynolds number can result in higher velocity and corresponding vorticity. Comparing the PIV and CFD results of different jet Reynolds numbers and protrusion relative depths when D equals 0.5 and 1.045, it is shown that their basic flow patterns are similar to that of D equals 0.318. The only change is that the jet diameter gets bigger comparing with protrusion diameter, so the shear layer between the impinging jet and surrounding fluid moves outward radially. And the position of wall jet caused by the turning of impinging jet moves outward radially at the same time. The whole protrusion is located at the stagnation region when D equals 1.045, then the wall jet caused by impinging jet has not yet contacted with the protrusion surface. Through the summarization of CFD and PIV research in impingement flow on target with protrusion, the flow structure conceptual graph of impinging jet is obtained as shown in Figure 2. The pressure coefficient Cp is defined as Cp equals 2 multiplied PIPA, rho 0 U0 square. Here pi is the static pressure on target surface, Pa is the atmospheric pressure, Q0, U0 is the density and velocity at jet inlet, respectively. As for the stagnation areas, Tarikov et al. Describes the pressure coefficient distribution as dome-shaped distribution. The pressure coefficient distribution is indeed parabolic distribution via the analysis in this paper. The reasons are as follows. The impingement target near stagnation areas is relatively smooth. Martin has deduced a radial velocity distribution which is still approximately established today. Nu m equals CRR, where CR is a constant parameter. Further deductions are as follows. Pi equals PO rho nu square, 2 equals PO rho multiplied square of CRR, 2 where PO is the total pressure. Substituting this formula into the definition of pressure coefficient, we can get a parabolic distribution. Figure 3 shows the pressure coefficient distributions of target surface when D equals 0.318. According to the characteristics of pressure distribution and flow structure, the flow of single impingement on target with protrusion can be divided into 4 typical regions: stagnation region, wall jet region 1, protrusion edge region and wall jet region 2. Stagnation region exists where R/D between 0 and 0.2. The impinging flow undergoes an intense deflection and starts to accelerate quickly in the radial direction. Wall jet region 1 exists where R/D is between 0.2 and 0.45. Wall jet is formed in this region. The flow accelerates firstly and then decelerates. Region where R/D between 0.45 and 0.7 is called protrusion edge region. The flow continues to decelerate and the flow separation is induced because of the adverse pressure gradient. And then the wall jet begins to accelerate slowly after the reattachment of the separation flow. By the way, the flow separation has not formed when d equals 0.1 because the adverse pressure gradient is very small. Wall jet region 2 exists in areas where R/D is above 0.7. The pressure coefficient distribution of target surface is not sensitive to jet Reynolds number and protrusion relative depth as shown in the figure. So the conclusion is confirmed that whole flow structure is single and it varies slightly with jet Reynolds number and protrusion relative depth. However, impinging jet flow structure is a little bit different when jet Reynolds number and protrusion relative depth change. The impact of jet Reynolds number change mainly concentrates in the area of protrusion edge region. For instance, pressure increment along protrusion edge region increases as jet Reynolds number increases due to the larger geometrical catastrophe in the transitional region between protrusion edge and target surface. Flow accelerates faster near stagnant region with the increase of protrusion relative depth and spherical curvature, which induces larger pressure increment near wall jet region 1 and protrusion edge region. Furthermore, flow separation is formed in the local region near protrusion. As shown in Figure 4 and Figure 5, the variation of pressure coefficient distributions with jet Reynolds number and protrusion relative depth when d equals 0.5 and 1.045 is almost same with that of d equals 0.318. And the only difference is that wall jet stagnation region gradually gets larger comparing with the protrusion diameter as impinging jet diameter increases. Particularly, impinging jet diameter is almost equal to protrusion diameter when d equals 1.045 and the interacting region of protrusion is just located in stagnation region of impinging jet, then impinging jet continues to accelerate. After passing through protrusion edge, a local peak of pressure coefficient is observed at protrusion edge region in the all cases. Velocity and pressure field is shown in Figure 6 when d equals 0.318, d equals 0.3 and Re equals 23,000 to explore the factors that result in the local high pressure peak. In the figure, the arrow indicates the direction of the velocity. The velocity decreases firstly and then increases in region 1. The flow direction changes at the same time. Velocity distribution in region 2 is similar to that in region 1. So the flow in region 2 is regarded as impinging jet with inclined angle, which is called secondary impinging jet in the present study. The local high pressure coefficient is caused by the secondary impinging jet. The wall jet developed in region 1 impinges onto the target wall and secondary impinging jet is formed. The velocity of impinging jet decreases because of interaction with wall resulting in the increase of static pressure. Besides, flow direction changes in this region, and pressure gradient gets bigger by the centrifugal force resulting from streamlines bending. Thus it is concluded that secondary impinging jet formed at protrusion edge region causes the local high pressure peak. According to the analysis above, the flow structure conceptual graph of the impinging jet towards protrusion target surface need to be improved and the secondary impinging jet should be added in the figure. The accurate conceptual graph is drawn as Figure 7. Based on Figure 2, blue arrows are added in Figure 7 to represent secondary impinging jet and the angle B stands for the turning angle.